This is part 5 of the AQA A-level chemistry topic, energetics. In the previous video, we looked at the principles that underpin Hess cycles, and now we're going to start looking at some of the calculations that you may face. In particular, in this video, we're going to focus on calculations where you've been provided with enthalpy of formation data. In a later video, we'll look at enthalpy of combustion data being provided. Okay. So, as always, I'm going to recommend that you try to work through each individual section, seeing how you go, and then you can review your answers afterwards and check whether or not you're on the right track. In this first instance here, I've really tried to break down Hess cycles into key steps that you can hopefully gain an understanding of why we're doing what we're doing. So have a read through. We've been given here some enthalpy of formation data for propanone and propan-2-ol. In the first instance, you're being asked to write an equation to represent the enthalpy of formation of propanone. So let's see how you do. Okay, so the first thing that you need to remember is that we have got to make 1 mole of the compound. That's what the definition tells us. So it has to be 1 CH3 COCH3 when we come to balance it. We also need to have the state symbols on here because we know that the definition tells us that reactants and products are in their standard states under standard conditions. So I've then got to consider the elements that I'm making it from. Well, I've got carbon, I've got hydrogen, and I've got oxygen. I have to remember that hydrogen and oxygen are diatomic molecules. Once I've got all of those in, I can then balance. You can see there my 3Cs, my 3H2s, and my half O2 will all come together to make CH3COCH3. But I'm still not going to mark if I'm asked to write this equation yet, because I must include all of the state symbols. So I've put those in as well. Okay, let's move on, have a go at these. So 2 more enthalpy of formation equations, and then a question about the enthalpy of formation of hydrogen. So in the first instance, again, it's formation. We know we're making 1 mole of propan-2-ol, and we know the elements that we're making it from. So I've got my 3C, my 4H2, and my half O2. I've got my state symbols in there. We are all done. If I'm asked to write the equation for the enthalpy of formation of H2, it's a slightly odd one, because H2, being made from its elements in their standard states, means we're making it from H2. And that potentially helps you to explain and understand the question in step 2. No value was provided for this, but if there's no change, our value is going to be 0. So 0 kilojoules per mole. Okay, going to move on, and we're going to look at building the cycle. So I've already started doing that here, and what I hope you can see is that we've got equations but not going horizontally left to right. I've got my 3C, 4H2 and half O2, my enthalpy of formation equation going up to propan-2-ol. And if I combine all of these, that provides all of the atoms, or all of the elements, sorry, to show the formation of both propanone and hydrogen. And I'm calculating X, so I'm going to put that one in. So now have a go at completing the rest of the calculation and see what you come up with. Okay, there are different ways of doing this. I'm going to go through the process of using the cycle. So if I know what my values are, my negative 248 for my formation of propanone, my negative 318 for my formation of propan-2-ol, I've now got the values for 2 different parts of the cycle. If we remember, Hess's law tells us that the overall energy change is the same whichever route is taken. So I'm going to identify what my 2 routes are here. And I've put that in with a green and a red arrow. I've got 2 arrows leaving from the bottom, and I've got 2 arrows arriving at the top right. So my green route is going to be equal to the red route. And if that's the case, I can now substitute my figures in. Negative 248 plus x is equal to negative 318. my green root is equal to my red root. I can then rearrange that to make X the subject. And if I've made X the subject, I can now do the simple maths to see that X is negative 70 kilojoules per mole. So there's a chance now for you to try a few more equations to work out their enthalpy changes. Have a go at this one. Okay, so you've been given the enthalpy of formation of ethene, you've been given the enthalpy of formation of dichloroethane, you've not been given the enthalpy of formation of chlorine, but that one will be 0. So you can see where I've taken the data from. I've built my cycle, I've got my enthalpy of formation of dichloroethane, I've got my enthalpy of formation of ethene and chlorine, I've written my equations out and I've put them in the cycle form. I've also put the figures directly in, and you can see we've got 2 of them and we have 1 left over. So let's identify the 2 roots. Well, it's going to look quite familiar to the last one actually. Both of my roots start at the bottom, both of them end top right. I have this arrow and the value will be equal to this plus this. So that then allows me to put my figures in. 52 plus X is negative 170. And I can then rearrange that to make X the subject, which gives me a value of negative 222 kilojoules per mole. Okay, let's try another one. Once again, you have got the enthalpy of formation provided, but you've got enthalpy of formation for all 3 of them provided: the ethene, the hydrochloric acid, and the chloroethane. So I'm going to complete the cycle. I've got my 2C, my 2.5H2, my half Cl2, enthalpy of formation going to here. And actually, if I separate out the enthalpy of formation of ethene and HCl, it needs exactly the same things. Now I've got my X, this is the one I'm working out, but you can also see, because I've got 2 enthalpy of formation values on the left-hand side, it's the sum of them, so it comes to minus 40. My chloroethane, negative 137. Now, I have now clearly got 2 roots again. And as always with enthalpy of formation, data provided, they're starting at the bottom and they're ending at the top right. So I've got my red root and my green root. You can see which data I've used to put in. And then I'm going to put my information into an expression. So I've got my negative 40 plus X is negative 137. Going to rearrange that to make X the subject. And that's going to allow me to work out that X is negative 97 kilojoules per mole. So let's look at another example. On this one, no enthalpy of formation of zinc, no enthalpy of formation of copper, because by definition they are 0. My enthalpy of formation equations, starting at the bottom and going up, 1 Zn, 1 Cu, and half an O2, and that works the same on the other side. So I've got my 2 roots, I find the data that I need, I've got that highlighted here, and I'm going to put those in. I've got my X that I'm calculating, I've got my negative 157, and I've got my negative 348. So I can now write out my expression. Once I've got that, I can rearrange it to make X the subject. And once I've done that, I can calculate X. And X comes to negative 191 kilojoules per mole. And got one more example to work through on this video. So this is lead nitrate thermally decomposing. So we're going to need to find all of the enthalpy of formation information on here. And we have got our PB, got N2 and 3O2. Be mindful of the brackets when you're looking at these to make sure you get the correct number. And then you find the data that you need, and you can see here that we have got our lead nitrate, negative 452. We've got negative 217 for the PBO, but look really carefully, we're making 2 NO2, so it's twice the enthalpy of formation value. So that means it's not going to be plus 33, it's going to be plus 66. And one of the common wrong answers you might get with this question will be 33 away from the true answer. And that will drop 1 mark off the exam. the question. Okay, once I've got all of that in, I build my two roots. And once I've got my two roots, I can put those into an expression. Negative 452 plus x is equal to 66 take away 217. Let's rearrange to make x the subject. Once I've done that, I can easily calculate x, and I get 301 kilojoules per mole. And I have put the positive in there just to show that I'm recognising it's endothermic. And if you think about it, with a decomposition reaction, breaking one compound down into multiple species, it would make sense that that would be endothermic. Okay, that takes us to the end of this video. Thank you for listening.